This is what happens every time I try to Google Mihao Yellow Submarine. That's I shouldn't do that. So Musty Thoughts. That's where you want to go. Mihao. So it is. Let me show you. So I went through that pretty innocently. Because you know, a couple weeks ago I was basically doing a bunch of videos. I'm at the airport right now, by the way, so it might be a bit loud. I'm sorry for that, but I hope I did a couple of tests, and it seems like at least my voice comes through in an understandable way. So, and you know what kind of caught my attention was when you were running through an example. Oh yeah, Ryanair flight right now. Anyway, where was that? What was that? What was that? Give me a second. Why I can't find that? To London Stansted. So basically, this is just distracting me. Give me a second. Now here, exactly. Oh, here you go. So maybe I have to go one step. Oh, this is here. So we need to measure our circuit many times and then substitute every 0 with a 1 and every 1 with a -1. I was like, what? What? Why? And so this is one thing. Another thing is I've been reading the quantum information. I think it's what's the exact title from Nielsen, like Mike and Ike, or Ike and Mike. I don't know how what's the sort of the friendly name for the book that everyone's reading. And basically, there's a bunch. I'm in the process of reading that, and I'll do a review and all that stuff, and sort of based on my experience, etc. But there's like an entire chapter about in the very beginning about measurement. That's another thing. So I'm trying to kind of like. I don't know if I can just say itty bitty because I need sort of a blank. This is let me zoom out. So one thing here was it's the VQE from Mihao, from I'll call it like Musty Thoughts. Another thing that I'm trying to kind of connect here is Mike and Ike on measurements. The whole thing really started because basically the first time I saw something like this, right? It's when I was getting into VQE in the very first time. And I remember I even asked on Twitter, I don't know if I can find that. I might have bookmarked the tweet, I don't know. Bookmarks. Because Guillaume answered, I think this is one of the, I can't remember where that was. I probably can't even search for that. No. Maybe it's one of my tweets, but I tweet maybe not super often. But I have to clean up these bookmarks. There's definitely a lot of stuff in here that. I basically made a tweet once where I was asking, like, okay, how is it possible? Like, why would you be able to do phase estimation by just doing or calculating the expectation value? Because the first time I came across the term expectation value, I was super confused. It's like, what is expectation value? Then I realized that means sort of the average. But I understood at the time that this meant the average of your measurements. And so that kept confusing me, and I mean it doesn't stop me from farther going on with breaking down stuff and kind of trying to build the intuition. But it's something that now, because of all these different things kind of coming together nicely, basically I think I got a sort of a nice little picture about, okay, sort of a bit of an aha moment. It was like, okay, now I think I know what this whole thing, it kind of makes sense a bit more, right? So, and actually what triggered the whole thing is really this. So this is what I was reading this yesterday. I have no idea how I came up here. Oh yeah, because I was looking for observables. What is an observable? Because in Mike's book, basically, they talk directly, introduce the concept of an observable by just saying it's something, it's something you can observe and measure, right? But maybe because they don't give examples, then I'm stupid here. Probably it's just my fault, right? But it still feels super. It felt abstract. So it's like, okay, what do you mean? I mean, is it, because they go ahead and they just talk about like that's an operator, so that's an observable, and that felt a bit awkward. And then this, when I started reading this, it just struck me like it was like an observable is an operator that corresponds to a physical quantity such as energy, spin, or position that can be measured. And I was like, oh, and that started basically a whole chain process in my brain of like, wait a second, that's this, and then I kept reading, and it's like it kind of makes sense. For a K-state quantum system, observers correspond to whatever, blah blah blah, and so it says here basically that so what the outcome of a measurement, so what is the outcome of the measurement of the quantity represented by the observable m on a quantum state phi, I think it's phi. So to understand this, if you write it this way, and then basically they're saying that the result of the measurement must be some lambda j, which is a real number we read off our measurement device with probability aj squared, modulo squared, absolute value squared, not modulus. Moreover, the state of the system is collapsed into this, and this, as I read just this first page, and a bit of the second one, I was like, I think I get it. So basically, here's an example which is really neat, because it's like, for example, suppose that we measure a qubit we wish to measure a qubit in the plus and minus bases, with measurement results 1 and -1 respectively. I was like, oh, wait a second, 1 and -1. Here it says 1 and -1. Okay, now I start to get it. Because I originally thought that the expectation value was just you do 100 measurements and you calculate the average result of the measurement. And for me, a quantum computer or a QPU are the ones you can access, from IBM or whatever, or even if you just look at Quirk or whatever editor, you're just going to always measure and get zeros and ones. And so I was under the wrong assumption that this is what you're making the averaging around. I mean, there's just a bunch of pieces that brought the whole. Another thing that really catalyzed or helped me kind of crystallize that is David. I don't know why I'm even writing it this way. Wait a second. So David Kopchik has a really nice also article on. No, that's not. Oh yeah, that's it. He changed. Is this his URL? He has on VQE, and basically he has what he does is, which I kind of don't like, and because it just doesn't, or it stays at a really abstract level. So what they say is like, okay, let's have an example, right? So let's see that's what we want to measure the eigenvalue of, right? So he stays here, and because he doesn't go to the practicality of the algorithm, which is fine, the whole thing becomes a bit harsher or harder to understand. But there are a couple of things in these posts that help you or help me as well. So the first one is that I realized this here. I was like, wait a second, that is not how you calculate the average of whatever. So he must be doing some kind of decomposition of this in here. Then he talks about these being introduced before, of being sort of the measurement projectors, right? So, and this is also presented like that in a similar way in Mike and Ike's book. And so I was like, wait a second, this is really what a quantum computer measures, right? That's kind of a mathematical representation of what a quantum computing actually tries to measure. But it's still, it was still not super clear. So it's like, 'cause I'm trying to reason this in hindsight, and it's just like, if you would see it went through, I think it took like about 24 hours to really, it all sort of like a chain of different things, popping up in my head. Was like, oh, these, oh, and these, oh, and these. Now this makes sense. And so this was also and then I kept on reading. As like, this corresponds to a measuring observable m, and I was like, wait a second, you're constructing the measurement. You're constructing the observable. I was like, poof, that's mind-blowing. So you're telling, because what you're basically saying is, where did I did that? Where did I read that as well? Here somewhere. I don't know, somewhere there. I don't know if it was here. Maybe I just jumped over it too quickly. But So the measurement was specified. The measurement outcome with J was from the sequence of real numbers simply provide a way. Exactly, the sequence of real numbers lambda simply provide a way to specifying what the pointer of the measurement device indicates, so to say, for the Jth outcome. So I kind of realized, wait a second. So yeah, I mean, basically, the only thing a quantum, the quantum, like a quantum computing measures is something, right? It's whatever, spin, energy. And I was like, of course, I mean, that makes sense. And continuous, like a photonic quantum computer like the one from Xanadu measures position and momentum. A quantum computer that is based on superconducting qubits, probably, and I might say something really wrong here, is measuring the spin. Now, I think what the quantum computer is really getting as an outcome of a measurement, because the standard measurement that's built in the QPU on the quantum computer is basically along the Z or the Z observable, which I think what this means is basically you're going to measure 1 or minus 1. So you're measuring the spin being 1 or minus 1. And when you measure 1, you know that the state collapses to 0 because that's simply the way the system works. And when you measure minus 1, you know the system has collapsed to the state 1. And then the quantum computer makes the sort of mapping and says, okay, the quantum state 0 is a classical bit 0. The quantum state 1 is a classical bit 1. So, and that is why you need to. That is why you need to do what Michał is saying here, which is replace. Sometimes the scrolling breaks. I don't know if it's on. Whatever. So, but basically, that's why you got to do what you got to do here. That it's replacing the 0 with a 1 and the 1 with a minus 1. What confused me is the way Michał puts it. It's just like, oh yeah, because those are the eigenvalues of the Z or of the Z operator or observable, and that's it, right? And for me, kind of, I was missing kind of, you know, I couldn't connect that at that point in my mind. But this is the sentence, my man. This is the sentence that started it all. And then I was like, yeah, I mean, really, it's really crucial to kind of deeply understand how you can leverage that, because what this really means, because I first thought, okay, so what does it mean? This, like, why doesn't this mean at a practical level, at a quantum circuit level, why doesn't this mean I just prepare the state, then I apply that operator, and then I measure, right? Well, because you're not like, I was having the wrong understanding of a measurement, right? In the sense that you're actually measuring a spin, right? And so what you want to know here is you want to measure the energy. This H is you want to measure the energy. The fact that the observable is also an operator at the same time. That's just a technicality. But here what you're doing is you really want to measure the energy. And so fortunately, what the whole thing with the VQE says is you can formulate the energy observable, or you can build the energy observable as a function of the X, Y, and Z observables that are native in a quantum computer, right? And that's what Michał is doing here. So it's basically saying, you know, if this is the measurement, if this is the observable we're trying to construct, why did the scrolling break? It just sucks. If this is the observable we're trying to build, we're trying to measure. Again, it broke. Come on. The arrows work. So this is the observable, because this is the Hamiltonian. You can basically express that in that way, right? Which are then all composed of things that of spin measurements, so to say. You're basically defining and building your energy observable out of a linear combination of spin measurements. I might not be spin, but it's just my guess right now that the 1 and minus 1 are spins, basically. And that's what allows you to do what then the rest of the article tells you, which is, okay, build a circuit that allows you to measure that, another one that allows you to measure that, and then just add the results up, and that's it. Because you're basically translating a measurement, or you're translating something you want to measure in a kind of measurement that then matches what your quantum computer is measuring. But then I'm curious because then this probably means that the VQE, of course, it needs to be adapted based on the machine you're running it on, right? Um, like if you're running it on a quantum on a photonic quantum computer, it's going to be different because there you're measuring position and momentum. So it depends on how you're going to be encoding that. That's interesting. That's interesting. Yeah, but I think now I feel better that I kind of like I just basically explained what I had in my mind. That's definitely the thing here. Um, what else I wanted to mention something else. Oh, these announcements, they just keep distracting me. I wanted to explain something. I measure something else. But basically, what VQE really is come up with a way to generate a random state, or like a parameterize it so you can explore different states, and then just measure the energies. I was like, it can't be that simple, really. At an intuitive level, this is really what's happening here. It's prepare a state because basically what here they're saying is so one important observable of any physical system is its energy. The corresponding matrix or operator is called the Hamiltonian and is often denoted by H. The eigenvectors of its operator. So and here this was also it was even more clarified. The eigenvectors of this operator are the states of the system with definite energy, and the eigenvalues are the numerical values of the energies of these eigenstates. And that's why you in quantum chemistry or you're looking for to approximate the lowest eigenvalue. But really, that is what it means when you have a Hamiltonian. That's why to build Hamiltonians, I guess, at an experimental level, you really have to do a lot of playing around and try to figure out what are the states of your system and what are the energies associated to those states, and then with that you can build your Hamiltonian. Wait, but that cannot be this way, because if it's this way, it means that we already know what's the lowest. So I guess experimentally you basically determine the Hamiltonian somehow, but you still don't know really what the eigenvalue is, right? What the lowest eigenvalue is. Yeah, but the fact that it's a matrix. The fact that it's expressed this way allows you to then use a quantum circuit to say, okay, so how can I observe that, right? And so basically, the states. Suppose we take 10 to the power 6 qubits prepared in the state phi 1 and measure the energy of each of 1 and make a histogram. Yeah, I cannot see figure 1a, so I don't know. But now suppose that we prepare this and we measure each of their energies and make a histogram. How does it look like? So figure 1b, I also cannot see this. Ask yourself, is phi prima prime, I don't know, a state with well-defined energy? The answer is no. I guess the idea is because it's not an eigenstate of the Hamiltonian operator, so only the eigenstates have well-defined energy. This means there are and then this is this is what just killed the whole thing. Like, even though a given state phi might not have a definite energy, we can still ask the question, what is the expected energy of this state? And that is just like, bam, here we have it. So this is, I don't know. You know, I still don't feel like extremely confident with this, but this whole chain of different bits and pieces out there kind of helping to connect all those dots really felt like a good, interesting moment. Yeah, so basically that's why you want to calculate the expected energy, because basically you're quite sure that you can be quite certain that this thing is not an eigenstate of your Hamiltonian, because you prepared that kind of randomly. I mean, you start randomly and then you basically try to minimize and change the parameters, but that's it. So what you're only trying to find is you're trying to find a state that has an expected energy value that's as low as possible, because the variational theorem basically guarantees you that, you know, the lowest is always the lowest eigenvalue, so you can't get lower than that, which basically means that a minimization approach is what you want to do, because it means, you know, it doesn't matter how deep you go down the hill, whenever you find your minimum, local minimum, then you can be sure that yeah, it's an approximation to that global minima. But basically, that's all what VQE is. It's just start with a random state, energy state, calculate, try to observe the energy of that, try to calculate the energy, and then minimize, and that's it. So and that's why I said I think it's more than it's more than just measuring zeros and ones, and that's one of the big differences between classical computing and is that here you're really simulating, you're really building a system like a quantum system, and so what you want to measure is crucial, and then the machine is going to be tuned to measure something specific like the spin or like the position or like the measurement, but sometimes you want to measure other things, right? So yeah, I don't know, I felt like I needed to do this video, despite the fact that I was really kind of getting into into Grover right now, into Grover's quantum search, but that really connected all the dots. Yeah, perfect. I hope the sound was good. I'm not going to be able to edit that, neither repeat this with the same energy. So then, yeah, I guess stay tuned for more.